So now we'll move on to our new material, which is sums of random variables. So let's suppose we have two random variables, x and y. And let's consider a function that depends on those. Now I'm going to go through a few different stages of developing this. One is that we'll look at the sum of those, and another is that we'll look at multiples. So I'm going to start with just a multiple. Just change the A to an alpha, noticing that the letter A keeps appearing in my sentences, and I can't really handwrite it in a clear enough way to tell that apart. So we just have a multiple of our previous random variable. And let's see what happens to things like expectation. So the work we just showed will give us the PDF of Z. Now we had different versions for continuous and discrete. It's going to be a bit easier to work with here if I look at just the continuous case. But the answers that we get at the end of all our work are going to be the same. So I'll work with the continuous case right now and just tell you that it's going to come out the same either way.
So Z is a continuous random variable.
Yeah. And I should emphasize that here they could be continuous or discrete. Doesn't matter. So I'll work on the continuous case, but we could also work on the discrete case. And the answers would work out the same. Okay, so when we were looking earlier, we had things where we had ax plus b. The only reason I wrote an alpha again was just because the letter a keeps coming up in these sentences. So what happened to that coefficient when I found the PDF of y, in this case it's z? The new PDF was 1 divided by that. And then we took the old PDF. And I had to convert from z into x.
Excuse me, Professor.
Yeah.
We have to take the absolute value.
And there's also that interval that we put at the end, but the interval that we put at the end only matters if we have finite integrals. And that actually would, if we had written our interval with the CDF being non-zero over some region and 0 the rest of the time, you would have noticed that when you plug values into here, you get non-zero only in that interval we wrote. Yeah?
Why can we not do z minus alpha over alpha?
If we look at the formula there, if I want to convert z into x units, I just take z over that. It's like b equals 0. So if you took the old formula, it would be a 0. It would look like this. let's say I want to compute the expectation. The expected value is you take an integral, you take your variable, and you integrate. Looking at this, my formula up there would be 1 over alpha, and then fx, z over alpha, dz. That does not look obvious how to integrate, so what we'll do is make a u substitution, because even though I don't know how to integrate this, I do know something about x. So I'm going to set u equal to z over alpha. Which if you look back here, z over alpha, well, that's actually x. So that's actually like an x substitution. So du would be 1 over alpha dz, which means dz is alpha d. So ez is now the integral of z 1 over alpha fx of u times alpha du. This alpha and this one cancel out, except for maybe a negative sign. So that would be the integral. Z doesn't work with du. So how do you deal with things sitting around like this when you do u substitutions?
Just move it outside the integral.
Well, we can't move it outside because z and u depend on each other. So what should I have done to this z in order to make it an integral with u's?
U alpha.
Okay. So z was actually alpha u. So something cancels out, and then we have another alpha left over. So that's integral with alpha u fx u. That should be the same as changing letters. It doesn't do anything. Let's just rewrite u as x. What is that integral called? We have another name for that integral. You had a homework due Monday night where you should have done that integral a bunch of times.
But the variance.
What's that? That's one of the things that was due Monday night.
That's expectation.
Yeah.
X.
That's EX. So that means that this is alpha EX. So if I multiply my random variable by a constant, my expectation gets multiplied by that constant. And actually this should be obvious because let's suppose, for example, well the math is not obvious, but let's think of a real world example. Let's say I took your exam scores and I doubled them. That should be great, right? What would happen to the class average? It would double. So that's what this is saying. If I double everyone's test score to get Z, then I double the class average. So it's a lot of math to say something that almost seems obvious. What if I added 5 points to everyone's test score? Then what would happen to the class average?
What's
Yeah.
5 divided by the?
Well, that's if I rescale things or something. What if I just took everyone's test score and I added 5 to it? How would that affect the class average? Right. So if I multiply by a constant, the class average is multiplied by that constant. And that's what we just showed here. If I add 5, I could do a similar argument, and we would see the class average goes up by 5. So if I want to put these all together, then more generally, if Z was AX plus B, sort of fitting the pattern we were just doing, then E of Z would be AEX plus B. Now let's suppose that instead of doing AX plus B, I change it to AX plus BY. Any guesses? Yeah?
Then, the expectation EZ would be AEX plus BEY.
Yeah, it seems like that might make sense, because when I did AX plus B, we found that I could just deal with X by itself and stick on that extra amount. If that had a Y, then maybe I can just deal with that separately. And in fact, that's true. These are two important results. I'm not going to try to prove that one. That one's a little bit messy. But it has to do with linearity of integration. If we thought of these as integrals, if I integrate this right-hand term, I get A times the integral as x's and B times the integral as y's. But an actual proof is a lot messier than that. They're just that simple statements. So you can look in the book if you really want to know why it's true. What about if we have variance? Rather than jumping straight to variance, let's look at expectation of squares. We'll start with the same starting point. Z was alpha x. What do you think might happen here? If I had E of Z, I had alpha EX. So I'm going to rewrite this in a way that might be a little easier for notes. So just going back to that, if Z is alpha X, then we found E of Z was alpha EX. And now the new part. Well, if I square that, I get this. What happened, what can I do to this to make it look more like the expression at the top? Kind of an open question that might have the wrong answer.
Use square root.
Square root is one idea. Maybe, like I said, my question is maybe too open-ended. So here I had a constant times x. Here I have a constant times x squared. When I had that alpha, it came out front. So I can do the same thing here. Okay, so I'm going to use this fact to look at something about variance. So if I wanted the variance of z, we know that's found by taking e of z squared minus ez squared. We just found that e of z squared is alpha squared ex squared. And this was alpha ex. Well, I can keep out that alpha squared. And so I get alpha squared times the variance. Why did that x square happen? Well, we saw the math, but another reason that we can expect a square is that if you recall, the variance was, you don't need to write this down, it's just a comment for you. The variance, recall, is the expected value of z minus u squared. So the thing inside the expectation is getting squared. So it shouldn't be terribly surprising that that stretching factor alpha got squared when we took variance. So that squares things. Which is why we had alpha going to the square of alpha. Now what if I had z equals alpha x plus b? There we had alpha x. So I'm not going to prove this one in quite the same way. I'm going to go back to the sort of intuition idea with test scores. So let's say this was your test score, x. And I doubled everybody's score, and I added 5 points. When I double everyone's score, then it affects how much your scores vary from the mean. Right? Variance measures how far things vary from the mean. When I double your scores, everyone's happy, but actually the people with the low score get less extra than the people with the high score. If I double 0, you still have 0. If I double 100, you get 200. So the range went from 0 to 100 to 0 to 200. And this is why the variance went up if I doubled everyone's score. What if I added 5 points to everyone's score? How does that affect the fluctuation of scores from person to person? It makes the minimum go up by 5, yeah. And it makes the maximum go up by 5. So the amount that your scores vary from average doesn't change. I just moved the whole class up, including the mean. So if I add 5 points to everyone's scores, if this was your scores, they just moved over, and now the amount they vary from the center hasn't changed. So this doesn't actually matter. So the plus b doesn't matter, only the alpha does. And then I'm going to write down one more formula here, and I'm not going to try to justify it. You can find the justification in the text, but I find that most people, if I prove it in class, it just causes more confusion than it helps. So for those of you who like proofs and like to know why things are true, on one of those, which is why I studied math. It is in the book, and I'd be happy to explain after class if somebody wants to know more. But if I have x plus y, I'll just write the e of x plus y at the bottom too. So when we looked at the expected value here, it was alpha ex plus beta ey. When we look at variance, it's going to get weird. So I'm going to write down an answer, but then say that it's only sometimes true. So when you look at a sum of variables, you add their variances, but only when they're independent. So why is independence needed? Well, let's say that we have a random variable x, maybe test scores in the class. I'm going to set y to be 100 minus x. So that would be how many points away you are away from 100, for example. So how many points you lost. And both of these have a meaning. If you take a test and you want to know your score, probably you don't want to know how many points you lost, but that's another way of giving a score. If I was a negative person, instead of saying you got 90%, I would say you lost 10 points. What's wrong with you? Okay, so these both vary. Test scores vary, and so the points lost vary. What about the sum? If I add these together, I get 100. So if we look at that variance formula, with alpha and beta being 1, the variance of x plus y is the variance of 100. How much does the number 100 vary?
0.
It doesn't, yeah, 0. So the variance of 100 is 0, because 100 doesn't vary, it's just a number. But the variance of x is not 0, that's whatever the class variance is for test scores. The variance of y would actually also be the same number, because the amount that your scores vary is the same as the amount that your deductions vary. So both of these variances are positive, but their sum is 0 variance. So that's where independence comes in. These are not independent. If I know what your score was, I know how many points you lost. But if this was exam 1 and exam 2 and they were independent, then that formula works. So any question that you're going to have on the homework or in the future where you're asked about the variance of a sum, you need to comment on independence. If you don't mention independence, there's always some deduction. Okay, so let's see an example. So let's suppose that on exam 1, this isn't true, but let's say the average was 90 points with variance 25. Now variance is a quantity that's written down a lot, but it's not actually interesting. The square root is the interesting one. This is a 5-point standard deviation, which means that the scores are pretty tightly around 90, if this was correct. Say on exam 2, the average is 85, and the variance is 100. And again, variance is not the real quantity that you care about. The square root of this is what you really care about. So a 10-point standard deviation is actually considered ideal on a test. A perfect test has a standard deviation of 10 points and a mean of whatever it is you think the mean should be. So I will let X represent scores on exam 1. And Y be scores on exam 2. Then X plus Y over 2 is the average of the two exams. Now I've been writing things with alpha X and alpha Y, so I'll rewrite this as 1/2 X plus 1/2 Y. Okay. What is the average of Z? I will do this properly with math, but before I do it properly with math, if I had asked you at the start of today, based on these two scores, what's the class average going to be? I think that many people in the class could have made a correct guess. So if I told you that's the average on the first test and that's the average on the second, what would you guess the class average is between the two exams? Yeah. Our natural guess would be 90 plus 85 over 2. Now let's, yep,
What's that variance for exam 2?
100. And I'm writing it down as variance because that's how we learn things now, but like I said a few times, really you want to look at the square root of that. Okay, so that's our guess. Let's see if that's true. So the expected value of Z is the expected value of 1/2 X plus 1/2 Y. And the formula we saw earlier said that would be 1/2 dx and 1/2 dy. And the reason for that is that this was what was called alpha, and this was beta. And we were able to take the alphas and the betas out and separate the sums. So that's 1/2 of